It's my pleasure to present to you today some of the progress that my advisor, Ravi, Chugh, and I have made on combining programmatic and direct manipulation. We're probably all familiar with what you see as what you get interfaces, like this presentation software here. These interfaces let you just directly manipulate the objects on the screen. So you can just click and drag and move, and the object goes where you want it to. And this direct manipulation, of course, is not just limited to presentation software. Drawing applications and document creation software as well let you simply click and drag to move the objects that you want. So in fact, pretty much every single creative application on computers these days is interfaced by direct manipulation. But there's at least one important computing application that you really can't do well by direct manipulation, and that's programming. Specifically, general purpose programming. So today, for the last 60 years, general purpose programming has been primarily a text-based activity. And so that means once you've typed up your program and you see that there's something wrong in the output, you can't just change the output directly to fix your program. So maybe we could figure out a way to combine programmatic and direct manipulation so that when your program produces bad output, you can just directly manipulate it, and then your program is automatically repaired for you. And this sort of combination of direct manipulation and programmatic manipulation would be really great, not only for programmers to make them more productive, but also for people who aren't programmers, because it would give them some access to the power of programming. So combining programmatic manipulation and direct manipulation sounds like a good idea. How might we go about doing it? One way would be to start with a direct manipulation system and then maybe add more and more programmatic features to that. Some systems have taken this approach. A couple notable recent examples are Brett Victor's Drawing Dynamic Visualizations, as well as Toby Schachman's Apparatus. And these systems are effective for a number of tasks, but the underlying representation is not a full, complete programming language, so you don't get the full power of programming. So instead, we might take the opposite approach. Why not start with a complete text-based programming language and all of its power, and then just increase its power by adding more and more direct manipulation features to it? So this is the approach we took in creating our programmatic vector graphics editor called Sketch and Sketch. In Sketch and Sketch, a user types up an SVG a program here, and that program draws SVG pictures. And once they have a picture, in our prior work, we showed how you could directly manipulate the output. For example, here we're moving the shapes, and Sketch will figure out which numbers it should change in your program to match your mouse movements. So you can move the shapes as well as resize them here. So this was an important milestone because now you can actually do some direct manipulation of your programs. But there was one limitation, which is that we didn't have any tools for drawing shapes, which meant that you still had to start by typing up your entire program. And programming by typing is hard. So a goal of this work is to see if we can relieve some of that typing burden and see how much of these programs we can build just by using our mouse. So to think about how we might do that, let's think about the development process of writing a program that draws a picture. So your first goal, if you're going to sit down and write one of these programs, is probably just to put some definitions into your program to draw shapes. And then after you have the shapes on the screen, they may not be in the right place, but now you'll go back through and refactor your program to encode the different relationships between the shapes. And then once you've done that, maybe you want to take your design and turn it into a reusable abstraction. So what we've done is we've taken this model and used that to add new tools to our Sketch and Sketch editor. So in this work, we now have tools to draw shapes, tools to declare the relationships between your shapes, and tools to build abstractions out of your design. So I'm going to demonstrate these new tools for you, and the way we're going to do it is we are going to build a program here that draws our Sketch and Sketch logo, which is this white stylized lambda symbol on a black background. And our design is going to be parameterized so we can quickly reuse it in a number of different variations. And finally, we're going to be able to do this without having to type a single line of code. So let's switch over to the demo. Okay. So here's the Sketch and Sketch editor. It's just a web application running in my browser. On the left side here is the text box where you can write code like normal. This is just a simple little functional language. There's nothing very special about it. On the other side is where our output will appear and where we can directly manipulate our drawing once we have it. Okay, so if you were going to type up your program, your first step would be, okay, let's put some shape definitions in here. So I'll demonstrate what you would do by typing at least. You'd probably go in here and say, I need a rectangle, so you have to remember the library function for the rectangle, and then you have to remember what its arguments are. I think it's color, I think an x and y, and width and height, I hope. And then when you run the code, if we got it right, which we did, now we see our output. I mentioned that in prior work, once we had the shapes on the canvas, we could just directly manipulate them, so I'll show that to you. I can grab the shape, and when I move it, Sketch and Sketch automatically figures out to update these numbers in the program, the x and y. And of course, I can also change the width and height. And not just spatial features, but the color as well. We can directly manipulate. So that's how you might start if you were going to type up this program. But we want to do this without any typing, so let's go back to a blank canvas. All right. And then now we've added tools to Sketch and Sketch so that just like a traditional graphics editor, you can select the tool to draw boxes, draw on the canvas where you want the box, and then Sketch and Sketch automatically inserts starter code into your program to make the definition. So we can kind of see here that it's named that rect1, and it's put that rectangle into the shape list here at the bottom of my program. And inside the rectangle definition, let me move this over. You can see we have some local variables for the position of the rectangle as well as its color. And then the actual rectangle is made by this call to a library function, and it uses the various variables. So it gave us all that without having to type any code. Since making shapes is easy, let's just go ahead and draw the lines that we need. Okay. So now we've got the basic structure of our drawing. It's time to start encoding the relationships between the shapes. So let's think how you would do that if you were typing this by hand. The first thing was we probably want the end of this line here to be snapped to the corner of this rectangle here. So how we would do this by hand is we would say, okay, what are the numbers that control the end of this line here? It looks like it's this 56 and 116. And then what are the numbers that control, not yet, that control the corner of this rectangle here, and it looks like it's this 73 and 69. Maybe we can define a pair of variables and use that pair of variables in both locations. So let's go ahead and do that. Maybe we'll call this like the logo left and logo top. All right, and then we need to give it some initial values, so we'll go ahead and use the coordinates of the corner of the rectangle to start with. And then now to make sure that both of these shapes are in the same location, we'll use the variables in both places, both for the position of the rectangle and for the position of the endpoint of the line. All right, now that we've done that, we can see that our line and the corner of the rectangle are snapped together, and they stay snapped together when I move one of them because their positions are coming from the same numbers. All right, so that's how you would do it if you were typing, but we were going to do this without typing, so let's go back. In Sketch and Sketch, you can now simply select the points you want. And there's a button in the editor that says A equals B, and when I press this button, that instructs Sketch and Sketch to refactor my program so that these 2 points are always the same. And when I click it, we see that it's actually done the transformation I just did by hand. It's inserted 2 new variables, and it's tried to give them informative names based on where they came from. And then it's used those 2 variables both for the position of the corner of the rectangle, the position of the corner of the rectangle, as well as for the position of the endpoint of the line. Okay. So now we can see that declaring relationships becomes very easy. So we can go ahead and snap the other ends of the lines to their respective corners. Just like this. And then the last thing we need to snap together is this endpoint of the line with the midpoint of this line here. Now this is a little different because if you were going to type this out, you would discover that the midpoint of this line is not actually a single number in your program. You would have to write out the math for the midpoint. Happily, Sketch and Sketch knows about midpoints, so I can just select both points, tell Sketch and Sketch to equalize them, and if we look in our program, we'll see that it's actually inserted a calculation for midpoint. It's actually inserted a calculation for midpoint for us, adding together the numbers and cutting them in half. So that makes this very simple. And we're not limited just to equalizing spatial features. We need these lines to be the same color. So why don't I select the line, select its color slider, select the other line, select its color slider, and tell Sketch and Sketch to equalize them. And when I do this, we can see it's added a new variable for the lines. And if I change the color of one line, the other line also changes. We also want the lines to be the same thickness, so I'll quickly tell Sketch and Sketch to make the thicknesses the same as well. Okay. So now, once we make the background black, we have our initial design. Now, we said we wanted to build this into a reusable abstraction. So the first thing to notice is that our design so far is a bunch of top-level definitions in our program. Maybe the first thing we want to do is gather all of these definitions into a single definition. This is a lot like grouping in a traditional editor. So all I have to do is select each of the shapes, press the group button, and Sketch and Sketch automatically pulls all of these definitions together into a single variable called new group 4. I can't quite reuse this yet. To really reuse it in a programming language, I really need it to be a function. So to turn this into a function, I can select the entire group, and there's an abstract button here. And what Sketch and Sketch will do is it will choose some numbers from inside this definition to become parameters for the function. And then it also has to rewrite this function in terms of those parameters. But it will do all of that for us. So I'll just go ahead and do that. And we can see, indeed, it's selected some of the numbers to be parameters. As well as at the end of the program in the shape list, it has added the appropriate function call. So now we have it as a function. Let's reuse it. And the way we can do that is Sketch and Sketch notices that we've defined a shape drawing function at the top level of our program. So I can actually just go and click this little lambda symbol to switch to the lambda tool. I can select our new group function, and now I can just draw it on the canvas. And Sketch and Sketch automatically inserts new calls to our function into the shape list. And each of these calls to the function has a different set of parameters, so we can go ahead and change the colors and such of these different designs separately and resize them and so on. So this was our goal. We wanted to create a program that made our logo into a reusable abstraction. So let me switch back to these slides. So we've written our program, and we didn't have to use any typing. And the way we were able to do that is because of the new direct manipulation tools that we added to Sketch and Sketch. So let's quickly review those tools. Instead of having, when you wanted to draw shapes on the canvas, instead of having to write out all of your definitions by typing, Sketch and Sketch allows you to simply draw on the canvas, and it will insert the definitions into the program for you. When you want to declare the relationships between your shapes, instead of having to manually type in new variables yourselves, Sketch and Sketch will automatically encode the relationship for you when you select the points and tell it to equalize them. And then finally, when you want to package your design into a function, instead of having to manually convert your code into a function, you can simply select the group, select the shapes you want to group them together, and abstract them into a function. So these tools are useful for producing a number of designs, but there are a few limitations. I want to talk about those briefly and how we plan to address them. Now, I mentioned that Sketch and Sketch knew about midpoints and would automatically insert the midpoint math for you. But if you relate lots and lots of shapes in your canvas together, sometimes Sketch and Sketch puts too much math into your program, and now you can't understand it anymore. So in the future, we'd like to use a better simplifier. And it would also be nice if Sketch and Sketch knew about, say, a midpoint function and could insert a call to a midpoint function instead of having to put the math in every time. Right now, our abstraction tools require that your program be written in a certain way. You have to have a bunch of top-level definitions followed by a main expression. In the future, we'd like to relax that constraint so that we could refactor programs that are of an arbitrary structure. And finally, in all the different stages of development, there are often multiple different transformations that Sketch and Sketch could do to honor the actions that you perform. And so which one should it choose? Right now, we kind of just choose the first one. But in the future, it's probably going to be better if we give the user an option to choose when there's ambiguity. All right, so looking a little bit further down the road, right now, Sketch and Sketch is an environment for writing programs that draw pictures. And that means that some of our transformations are domain-specific, just for programs that draw pictures. However, because the underlying representation is a program, that means that some others of our transforms are actually general and can be reused for programs in any domain. And we hope to leverage this because we'd like to see Sketch and Sketch applied to many other domains, including general-purpose programming. So let me briefly mention some related work before I conclude. Besides the systems mentioned at the beginning of this talk, in the late 80s and 90s, there were a bunch of systems that explored programming by demonstration, where you would demonstrate each step to the computer to have it write your code for you. The trouble with this is that sometimes demonstrating step by step what you want your program to do is actually harder than typing it out by hand. So we've tried to focus on transformations that are harder to type. There are a number of domain-specific applications that use direct manipulation, but they also have an internal programmatic representation of your content. However, unlike our system, this internal programmatic representation is not a full programming language. There were a number of constraint-oriented systems that explored combining direct manipulation and programming. However, these require that there was a constraint solver running while your program was running. And we only do constraint solving to refactor your program, not for running it. And then finally, in the last couple of years, a number of systems have appeared that take the same approach that we have, where you start with a text-based general-purpose language and then add more and more direct manipulation features to it. These first two allowed you to manipulate strings in the output. And then Sean McDermott has some demos of a system that overlap with some of what we are doing, and I encourage you to check it out. All right. In conclusion, we start with the full power of a text-based general-purpose programming language and aim to increase its power by continually adding more and more direct manipulation features. Because of the tools that we've added to Sketch and Sketch, you can now write some substantial programs that draw pictures without using your keyboard at all. If you'd like to take a look at our system, we have a demo online, as well as some videos on YouTube. If you just Google for Sketch and Sketch, you'll find it all. Thank you.
We have time for one or two quick questions.
Hi, very nice demonstration. I'm wondering, what's really the difference between your work and Brad Victor's work, and also the paper published last year about object-oriented drawing, because all of the demos you do can be done in their system. It's a matter, what's the file, like in the object-oriented drawing system, the file is exactly what you showed there. Like all the shapes, the attributes, the relationships are preserved. Like you didn't really show what you can do in the, I don't understand why the programming, why didn't you show the power from the programming side?
Right, so I can answer the last question first. Why didn't I show the power from the programming side is that the focus of this work was to try and see how much of that program we could build just with our mouse. When you have a program, I'm just kind of assuming that everyone knows that when you have a programming language, you can do powerful things. So that's that question. As far as the difference from Brett Victor's work, what I showed there was you can draw on the canvas and it starts building up something that looks like a program, but it's not a text-based language at the end of the day. So you don't have the full power of a text-based language. So we're trying to say, okay, we have these text-based programming languages, and they're super powerful. And we have direct manipulation, and it's super powerful. Can we combine both of them without losing any of the power of the text-based language? So that's where we're going there. And do you remember who made the object-oriented drawing?
Yeah, I'm the author of it.
What's that?
I'm the author of it.
All right, well, we can talk afterwards about that. Okay. Thanks.
Hello. So a follow-up question. You mentioned that this doesn't, the code that you have linked to the direct manipulation side, it's not as powerful as a full text-based programming language. So I'm wondering, why do you have the limitation? What are the challenges behind that decision? Why did you choose to do it like that?
So the question is why do you start with a text-based programming language? Is that?
No, why isn't it as powerful as a full text-based programming language, as you just said?
Okay, like Brett Victor's work, why isn't it as powerful? So if you start with a direct manipulation system and then try and add programmatic features, oftentimes those programmatic features are limited. So I guess I would say I'm assuming that the fact that everyone who programs writes in text says something about the power of starting with a text-based system. So there's always things that you will be able to do in a text-based system that will be difficult to do in other modalities of interaction. So I think, yeah, I'm not sure if that's directly an answer.
It's okay. Thank you.